Hello everyone, and welcome to this video on graphing quadratic functions of the form f of x, or y, equals a times x squared, where a is some real number. Alright, so this is kind of a continuation of some previous videos I've done on function transformations, graph transformations. We talked about in the previous videos horizontal shifts, right, moving the graph left and right with a simple change to the rule for the function, or vertical shifts, moving the graph up or down, and those involved, just simple addition or subtraction. Here we have multiplication, right? So what's going to be going on in this video is I'm going to be starting off with the most basic quadratic function, just f of x equals x squared, and then changing the rule for x squared by simply multiplying it by some real number, some non-zero real number, and seeing what that does to the graph. Alright, so let's take a look at these. In my first couple pages, I'm going to introduce you to these function transformations where I take a rule and multiply that rule by a number. Alright, the first page is on transformations, and I've written all this out beforehand. And then after I go over these couple pages, I've got a couple examples. So function transformations or graph transformations, this page is on vertical stretching and vertical compressing. Alright, so stretching is, vertically is pulling all the points of the graph away from the x-axis, right? And vertical compressing is taking the points of a graph and pushing them toward the x-axis, right? So suppose we're given the graph of some function y equals f of x. In this video it's going to be y equals x squared that we're going to be starting with. But this rule that I'm writing here, these rules, when you cause certain transformations, this f of x could be any expression that depends on x. Y equals x cubed, y equals the square root of x, y equals 2x plus 5, whatever. But like I said, we're going to be doing y equals x squared to start. So suppose I'm given the graph of some y equals f of x and a positive number, right? So this first page, I'm going to talk about what happens when you multiply by a positive number only. Alright, so this letter A represents a positive number. It's greater than 0. Alright, well, different things happen if A is greater than 1, or if A is, between 0 and 1, less than 1, but still positive. Alright, if A is greater than 1, so say 2 or 3 or 5, and I take the rule the way it was, or I leave the rule f of x the way it is, but then multiply outside of it, multiply the entire original rule by a. Alright, so instead of y equals f of x, I'm now looking at y equals a times f of x, 2 times f of x, or 5 times f of x. Well, the graph of this new function with this new rule, a times f of x, will be the graph of y equals f of x. It'll be the graph of the original vertically stretched, and they say by a factor of a, right, by this number a. And really what you're doing, as I wrote down here, is you're multiplying all of the y coordinates of the original graph by a. So if you take, look at my example picture here, this graph here, the blue is, f, the original, say, the graph of the original. And then I multiply all the y coordinates by 2 or by 3 or by 5, by some number bigger than 1. All the y coordinates of the blue will get larger, right? So all the points on the blue graph will be pushed away from the x-axis. The only points that wouldn't get moved would be the x-intercepts, right? Because if you multiply 0 by a, it's still going to be 0. So the only points that don't get moved by a vertical stretch are the x-intercepts. But every other point on the blue graph, again, gets, you multiply the y coordinate by a, and if a is bigger than 1, the points go further away from the x-axis. You get a vertical stretch for the graph of this, y equals a times f of x, where a is greater than 1. Now if a is less than 1, but still positive, right, so say a half or 2/3 or 1/5, right? Then I do the same thing. I take my original rule f and multiply it on the outside by a. Well, again, you're just doing this to the y coordinates then. You're multiplying all the y coordinates by a half or a third or 2/5, something less than 1. And that will like shrink all the y values. So all the points will be, moved closer to the x-axis. You get a vertical compression. All right, the graph will be vertically compressed, by this factor of a. So a little example picture here. So say again, this blue parabola looking thing is the graph of my original function, y equals f of x. And then I multiply all the y coordinates. I multiply this original rule by some number less than 1, like a half or 2/3 or whatever. All the, so all the points are now pushed closer, right, to the y-axis. The blue is pushed toward the x-axis, sorry, and we get a vertical compression. And just as with a vertical stretch, the only points that would not get moved, would not get pushed in, would be the points that are already on the x-axis, right, the x-intercepts. Because if you multiply, the y coordinate of 0 by a, it's still going to be 0. You'll still have x-intercepts. All right. So vertical stretching, vertical compressing doesn't affect x-intercepts. So I'll make that point. Okay. All right. So that's vertically stretching and compressing. Right. Multiplying, taking some rule and multiplying by a positive number, whether it be bigger than 1 or less than 1, gives you a stretch or compression. Then the other transformation we're going to have to know about before I get into my examples is, well, what if I multiply by a negative number? All right, this was a positive number page. I multiplied both, the function f by a positive number a. Well, really you just need to talk about what happens when you multiply by -1. Okay, because if I say, well, what happens when I multiply by -5? Well, you can multiply it by 5 first, right? Do the positive thing first, the vertical stretch or compression, and then multiply it by -1. All right, so really to talk about multiplying a function by a negative number, you need to combine these, multiply it by the positive and then multiply it by -1, to make it negative. So this is function transformations, graph transformations, and this transformation is a reflection about or across a reflection about the x-axis, right, the horizontal axis, which I've pointed out here in my little drawing. So if we're given the graph of, y equals x squared, y equals x cubed, y equals 2x squared plus 5, whatever, y equals f of x, some function of x, then the graph of y equals -1 times f of x, right, I take the rule the way it was, and just simply multiply on the outside by -1, multiply the whole rule by -1. That will be the graph of the original reflected about the x-axis. It'll like flip over the x-axis. And again, all you're doing is multiplying the y coordinates by this number, by this -1. So I got a little sample picture here, and say this blue graph is the graph of the original, y equals f of x. And I multiply all the y coordinates by -1. I multiply the entire rule by -1, giving me y equals negative f of x. And all the points on the blue graph flip over, go to the opposite side of the x-axis. You get a reflection across the x-axis and get this, upside down parabola here. And just as before, just as when I talked about multiplying by a positive number on the previous page, x-intercepts are not affected. All right, your x-intercepts on the blue and the red graph are the same points, because when you multiply 0 by any number, it's still 0. All right, so those are the transformations we're going to need to know about to get into my examples here. All right, so the first example, and in both of these examples, and I'll pull these pages back, I'll refer to them again later. My first example, and both of these have the same instructions where I'm asked to use the graph of y equals x squared to graph each quadratic function, and then label at least 3 points on the graph. Okay. Alright, so I'm going to make a table for this first one, where we're going to start off with y equals x squared, right, and then transform y equals x squared to get the graph of this, y equals 3x squared, or f of x equals 3x squared. All right, so I'm going to start with y equals x squared. And I'll make a table, and you've seen me do this y equals x squared table in other videos if you've been watching other videos of mine. And so input x, how the output's calculated, and then the ordered pair will be plotting, the point will be plotting. So negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. So I'm plotting these, these 5 points, and there's infinitely many points, so I'm just plotting these 5 special ones, and we'll draw the rest of the graph, once we see the pattern. All right, so I'll plot these points on my coordinate axes right now. I have my x and y axes drawn on some graph paper here, and I'm going to have it so that every square represents 1 unit. Alright, so 0, 0 is on there, 1, 1 is on there, 2, 4 is on there, negative 1, 1, negative 2, 4. Okay, and again, I'll just do this in this dark red color, and going up that way forever, and up this way forever as well. All right, there's the graph of y equals x squared. All right, so that's our starting point, and then we're going to be graphing, y equals. I want to do one transformation at a time, and there's really only one thing to do here. I'm going to change the rule x squared into the rule 3x squared. Well, that would be just by simply multiplying by 3. Right? So I multiply the rule by 3, giving me y equals 3 times x squared, and this is the f of x that we're given, right? F of x is 3x squared, that's this guy here. And when you multiply, when you leave a rule the way it is, right? When you leave a rule the way it is and multiply the whole rule by some number, you just multiply the y coordinates. Multiply the y coordinates by that number, the y coordinates of the original rule. Right? So multiply the y coordinates by 3, or if you're talking about transformations, remember this is I'm multiplying by a positive number here. Right, going back to my first page, and it's a number bigger than 1, right? I'm multiplying by 3. So they would say that this new graph is going to be our old graph, y equals x squared, vertically stretched by a factor of 3. Right. So we could say the graph gets vertically stretched by a factor of 3. Okay, well I'm going to just add this to my table. Alright. So I have my inputs x, right? So I'm going to use the same inputs. Then over here, how do I calculate y? F of x equals 3x squared. I guess I should use f of x because that's what was given to me. F of x equals 3x squared. And then the ordered pairs we're going to plot, right, with input x, output f of x, right? Output y, same thing. Well, when x is negative 2, right? Negative 2 squared is 4, times 3 is 12. And you see exactly what I was saying down here. You took the y coordinate from the original graph, 4, and just simply multiplied it by 3. 4 times 3 is 12. And going through these, 1 times 3 is 3. 0 times 3 is still 0, right? Remember I said earlier, x-intercepts won't be affected by multiplication. 1 times 3 is 3. And 4 times 3 is again 12. And you can double check. When I plug in 2 in for x, 2 squared is 4, times 3 is 12. When I plug in 1 in for x, it's going to be 3, and so on. So the ordered pairs I'm plotting are, input negative 2, output 12, negative 1, 3, still 0, 0, positive 1, 3, and 2, 12. I'm applying these points. So notice we still have 0, 0, right? Again, the x-intercept's not moved, so that point's still on the graph, right? The origin. Now I have, negative 1, 3 instead of negative 1, 1. So there's the stretch, right? By a factor of 3 times. Points on the graph are pushed away from the x-axis, stretched out vertically. You have positive 1, 3, this point here. 2, 12. So 5, 6, 7, 8, 9, 10, 11, 12. 2, 12, this location, and then negative 2 for x, 12 for y, that location. And I'll draw this in, like this light blue color. Still a parabola though, the nature of the shape of the graph doesn't change, it's just getting stretched out. Alright, so like this. Okay, it's not a great graph, but still a parabola shape. Alright, it's this original red graph, drawn where all the points on the red are now 3 times the distance from the x-axis, right? All the y coordinates got multiplied by 3, and you get this vertical stretch by a factor of 3. Right, and I'll write that on the graph again here too. Vertical stretch by a factor of 3. And if there were points on this side, which there aren't, but if there were points on this side of the x-axis, they'd get pushed down by a factor of 3. The points on the red graph were all above the x-axis or on it, but the ones that were above the x-axis, they got pushed up by a factor of 3. But you're getting this stretch, right? Things are stretching away vertically, away from the x-axis. Great. Okay, so for the next example, all right, I'm not going to do the table this time. You can always make a table, right? When you're graphing functions or graphing any equation, you can always make tables and figure out solutions to equations, plot points, and then once you have enough points, fill in the pattern, fill in the rest of it. But for this next example, I'm actually just going to go and take one transformation at a time. If you can recognize the transformations that would occur while graphing, you don't need to make a table. Oh, and I guess I should have labeled some points, right? It said to label at least 3 points. Okay, so there's the point 2, 12. Here's the point negative 2, 12, and there's the point 0, 0 on the graph. There's 3 points on it, and then 1, 3, negative 1, 3. Okay, I mean you saw them in my table, but and this is y equals 3x squared, or f of x equals 3x squared. Right? Cool. All right, so my next example. This first one I took y equals x squared, I took the rule for x squared and multiplied it by a positive number, and we saw this vertical stretch, and it was a positive number bigger than 1. For the next example, I'm going to be graphing this. F of x equals negative 1/4 times x squared. Alright, so as before, I'm going to start with y equals x squared. Alright, so let me write that down over here. I'm going to start with y equals x squared. I'm going to do that in this red color. So you got 0, 0, 0 squared is 0, 1, 1, negative 1, 1, 2, 4, and negative 2, 4. And we're looking at this parabola again. Right. So here's y equals x squared. Great, as you saw in the previous example. Alright, so now what I'm going to do is I'm going to take this rule, for x squared here, this function y equals x squared. I'm going to take the rule for x squared and change it, transform it, but doing one step at a time, one transformation at a time, until I get it to look like this. So notice it's multiplied by a negative number, right? I keep the rule the way it is, x squared, and multiply it by a negative. Well, I mentioned before, what you're going to do in that case to see what transformations occur is first you multiply by the positive number, right, causing a vertical stretch or compression, and then you simply multiply by -1, right, to make it negative, and that would cause a reflection about the x-axis. Okay, so let's do that here. So I've noticed, there's this -1/4 in front here. So first I'm going to multiply the x squared by +1/4. Right, so I'm going to multiply the x squared, the rule, by +1/4. So what's that going to do? That's going to cause a vertical compression, right, back to that first page. Because if I multiply by +1/4, right, that's the second case here. It's a number between 0 and 1. So the graph of this 1/4 x squared, y equals 1/4 x squared, will be the graph of y equals x squared, vertically compressed by a factor of 1/4. All the y coordinates are going to be multiplied by a quarter, and you'll see in my graph that all the points from the original will be moved, pushed closer to the x-axis. You'll be compressed, pushed closer to the x-axis vertically. So this is going to cause a vertical compression by a factor of 1/4. Or you just, again, multiply all the y coordinates by a quarter. I'll write all three of these things, because they all mean the same thing. Multiply the y coordinates from the original graph by 1/4. Alright, so we're looking at y equals 1/4 times x squared, right? Leave the rule the way it was, multiply by a quarter. Alright, so let's see what points would be on there. Now 0, 0. Remember, x-intercepts aren't affected by this multiplication. You multiply y coordinate of 0 by a quarter, or you plug in 0 for x, you're going to get 0 back. So 0, 0 is still on it, the origin. Instead of 1, 1, you'll have 1, 1/4. I'll actually label this. Here's the point. 1, 1/4. And instead of -1, 1, you multiply the y coordinate by a quarter, you'll have -1, 1/4. Right, and the same level as this 1, 1/4 over here. See how the point is on the red graph, on the original graph, is compressed vertically, right? It's pushed down toward the x-axis, okay, pinched. Then instead of 2, 4, right, multiply the y coordinate by a quarter. What's a quarter of 4? That's just 1. So you also have this point 2, 1 on the graph, and then same thing goes over here. -2, 4 multiplied by a quarter, there's -2, 1. And I got enough points here. It's still a parabola shape, right? Doing this multiplication by a positive number, taking your original rule and multiplying by a positive number, it doesn't change the general shape of it. It's still going to be a parabola. It's just, the points are now compressed vertically. They're pushed toward the x-axis, and I'm getting this picture here. Right, something like this. And there's y equals, 1/4 x squared. And do you see the vertical compression, right? All the points above the x-axis got pushed toward the x-axis. And if there were any points below the x-axis, they would also have gotten pushed toward, they would have gotten pushed up by a factor of 1/4, right? All the y coordinates were multiplied by a quarter. All right. And then from there, got one more step. All right, I multiplied by the positive 1/4, right, to give me 1/4 x squared for the rule. That did the compression by a factor of 4, 1/4. Now I just need the negative sign, right? So I'm going to take this rule the way it is, and I'm going to multiply this rule. Multiply the rule, the 1/4 x squared, leave it the way it is, and multiply it by -1. That'll make it into -1/4 x squared. And what does that do? Right, and again, back to one of my earlier pages, multiplying, taking a rule the way it was, leave it the way it is, and then multiply it on the outside by -1, causes a reflection about the x-axis. It flips all the points across the x-axis. Again, you're just multiplying the y coordinates by -1. So I'll write all that. So this will cause a reflection. It'll take our blue graph, it'll take the previous graph, y equals 1/4 x squared, and it will reflect about the x-axis. In other words, we're going to be multiplying the y coordinates by -1. Right. So we're looking at y equals, the 1/4 x squared times -1, making it -1/4 x squared, and this is what we wanted. This is the f of x. Right, that was the -1/4 x squared up top. Alright, let's see what those points look like. So 0, 0. Still 0, 0. So the origin is on this graph. 1 +1/4. Multiplying the y coordinate by -1 puts it at 1 -1/4. Now this is going to be kind of cluttered here. So I'm going to draw this again on the next page, on another page separately. But there's -1/4. Same thing over here, -1 1/4. Multiply the y coordinate by -1, reflects me across the x-axis to -1 1/4. Then 2 1 goes to 2 -1. -2 1 goes to -2 -1. And again, it's this blue parabola, but flipped across the x-axis. Right? It's still got the same shape, just flipped across the x-axis. So there's y equals -1/4 x squared. All right. Great. And like I said, that's a little cluttered there. I'm going to draw this one more time on a separate graph. Right. So we're looking at graphing f of x equals -1/4 x squared. Got my axes up here already. So there was 0, 0 still on it. Then 1 -1/4. A little small there, right? And then -1, also -1/4 for the output. Then 2 -1, and -2 -1. Right? It's that same parabola shape, but just opening downward. Right? And labeling some points here. Again, there's 0, 0. There's 2, 1, and over here's -2, 2 -1, sorry, 2 -1, and over here's -2, -1, and there's at least 3 points labeled on that graph. All right. And as always, you could make a table if you wanted. Right? You're graphing a function, graphing an equation. You can always make tables if you don't remember the transformations exactly, and go from there. After you've plotted enough points, hopefully you see a pattern and you can draw the rest of the graph. Alright, so the keys to take away from this video. 1, if you take the graph of a function, you take the rule for the output, x squared, 2x plus 1, whatever, and multiply that rule by a positive number. If that number is greater than 1, you cause a vertical stretch. If that number is less than 1, you cause a vertical compression. And if you take a function rule like x squared or x cubed, and multiply it by -1, that just reflects the graph across the x-axis. Alright, so those are the keys to take away from this video here. So look at those first 2 pages I had up again if you want to go back. Alright. As I like to say at the end of these videos, do the best you can to learn the material on your own before you go looking for help. I have found over the years that people that take the time and the effort to learn something on their own tend to remember that better and also remember the material for longer, and they're more proud of it. So, read the book, read the material, of course, read through the author's examples, perhaps even try to work out the solutions to an author's examples before you see how the author did it, and then compare your work with the author's and see if you can learn from some mistakes there. Obviously, practice tons of exercises, practice problems, right? That's the only way to get better at anything is practice. check for solutions to those if they're ever made available to you, so you can check yourself, see how you're doing, keep track of your progress. And don't just give up on a problem after 1 or 2 attempts. Very often in mathematics there are several approaches that'll work for any particular problem. So if after several approaches at a problem you're still having trouble, I would suggest you actually go back and read the material again, maybe even a third time, more slowly, more deliberately. Take good notes. Because if you've been working on problems as you should, you probably have a better idea as to what the author wants from you in that section, what the author expects of you. You'll see more about what the author feels is important from that material. So when you go back and do a second reading or even third reading of the material, you'll know better what to look out for. You'll catch more the things that are considered important by the author a little better. Maybe even catch things that you didn't catch the first time you read through, and it'll make working on the problems that much easier. But if after that, if after several read-throughs of the material and several attempts at the problems you're still having trouble, still not clicking for you, it is not a sign of weakness whatsoever to go asking for help. That is what other people are there for, to help you. So ask a teacher, a tutor, a friend, someone in your class who you know knows the material well and is willing to help. Look for supplemental materials online. There's tons of it out there. Look for videos online. There's tons of those too. Videos like this one, or plenty of other videos out there that are better than this one. I assure you they're out there and they're easy to find. But just keep at it. Stay persistent. Keep practicing. Don't give up. And above all, and I think this is the hardest thing for most people, stay positive. Believe in yourself and your abilities to work through your struggle, even in those moments when you're struggling and failing and making mistakes and getting frustrated. It's in those moments of struggle and failure and frustration that you have the opportunity to learn the most, and also learn the most deeply. Because if you can persevere, if you can push through your frustrations and actually learn how to fix your mistakes, you'll remember that material far longer and far better than someone who just got it right the first time and breezed through it and never gave it a second thought. Alright, so stay persistent, keep practicing, keep at it, stay positive, and don't give up. And I just know you'll get it. And thank you very much for watching.